So, hello, welcome to the Astrobiology lecture course network, the new series that starts in this winter semester 2012-2013. My name is Gerda Horneck. I'm from the DLR, Institute of Aerospace Medicine in Germany, and at the same time I'm president of the European Astrobiology Network Association. So I first want to give you a quick lead through astrobiology. And one of the main questions of astrobiology is life a cosmic phenomenon? Or is life just restricted to one body in our universe, and that is the Earth? And I think we can share the opinion of one of the Nobel laureates, and that is Christian de Duve. And he said that life is a cosmic imperative, and that it emerges always at a certain stage of either cosmic or planetary evolution if the right environmental, physical, and chemical requirements are provided. But now the question is, what are the right environmental conditions, physical and chemical? And we will look into this later on. But that means that we have in astrobiology to study the whole evolutionary chain of events that finally leads to life. And that includes that we first have to understand how the elements that are necessary for life are formed in the evolution of our cosmos. That means the cosmic chemistry of the biogenic element. Then we have to understand how these elements combine to molecules. This is all abiotic, so these processes do not need life processes. And then finally, and that I think is still a black box, how life really originates, the great question. How it then starts evolution from first and finally evolves to higher advanced life forms, and then it might even distribute in the universe. So these are all questions which are tackled by astrobiology. Astrobiology is actually the study of the origin, evolution, and distribution of life in the context of chemical evolution. So that does not mean that we necessarily want to look for life beyond the Earth. That's one of the driving questions. But important is to understand the processes that lead to the origin, evolution, and distribution of life, not only on the Earth, but in the context of cosmic evolution. And for this, we need many, many different disciplines. And I've listed here a few: astronomy, planetary research, geology, paleontology, chemistry and biology, molecular biology, field sciences, many, many fields. And with this, all these groups have joined together in a kind of consortium to tackle the question and solve the questions, what is a universal definition of life? But of course, not all of these disciplines and expertise is available at one university. Or on the other hand, some of the representatives of this discipline are not so much interested in astrobiology. And so some European colleagues within the European Astrobiology Network Association came together and thought whether we can have such an astrobiology lecture course network, established that, and that finally was realized with the help of the European Space Agency and ESTEC. So now the European Astrobiology Network Association came into the game. And what is the European Astrobiology Network Association, EANA? It's actually an association of different astrobiology societies, communities, or interested groups in Europe. And it was created in 2001. And the aim was really to bring different fields of European researchers that are interested in astrobiology together. So that means all the different disciplines from astronomy through planetary research over geology, and finally physics, chemistry, biology, origin of life, all these groups to bring them together, and from the different countries in a loose network. And of course, we want also to attract young scientists to this interdisciplinary field of research. And I think the ABCnet is one of the activities that serves this issue. And then to popularize astrobiology to the public and to students. And we see here the website of the Astrobiology Network Association, and it is hosted by the University of Stettin, who are also members here at the ABCnet. Welcome to ABCnet. You see here the different countries that are at the moment joining ERNA, and that reaches really from Sweden, Finland, through Russia, Romania, Greece, Hungary, Austria, Czech Republic, Germany, Switzerland, Holland, Belgium, France, Spain, Portugal, and the United Kingdom. So it's really already a very pan-European network. And each of these countries have a national representative. I don't have the names here, but if you look at the website, you can find the names of all the national representatives. And if you are interested in learning more about ERNA and participating in the activities, you're welcome to visit the website. ERNA also holds annual meetings, annual workshops, and the next one will be next week in Stockholm. And you see here the topics which really cover all this, what you have also in your astrobiology network, ABCnet, extrasolar planets, astrophysics, astrochemistry, geochemical origin of life, origins and evolution of the biosphere. Then we look at the planets, whether they are habitable, and also the moons, and here are listed Mars, Titan, and Europa. So Mars as our neighbor planet, and Titan and Europa that are the moons around the giant planets. Extremophiles and early life is very important in order to determine habitability of a external planet, and also astrobiology on the International Space Station, which came up within the last years, and they are very interesting experiments. And you will hear also about many of these topics during this course. And in addition, the workshop has a student contest, which is called the Space Hackathon. And this is a competition by different students, PhD students, also undergraduate students who want to participate, present their work to a jury, and there will be at the end a award to the winner, and that is the Svante Arrhenius Award. And also there are travel grants provided to students. And here you see the website of the conference. During the fourth workshop in 2004, the group of people came together and discussed whether we should have such a network of astrobiology lectures, which are really at the university and a part of the university lecture plan. And the first started in 2005-06 in the winter semester, then 2007, 2008, 2009, 2010, and now we have the fourth series of this course. And as you know, it's a real-time teleteaching. And the scientific coordinator of this ABCnet is François Rollin from the University of Paris East, Créteil, and the technical management is done by Nigel Savage from ESA ESTEC. And if you want to read something about previous courses, the lectures of the first course are published in the book Complete Course in Astrobiology, and that's published by Wiley, and that appeared 2007. Now we come a little bit to cover astrobiology. Astrobiology, as I told you before, is really understanding the processes that lead to the origin of life through the cosmic evolution. So on the left side, we start with a Big Bang, and you should see here that the axis is somehow not a regular axis, so the time scale is here and at the beginning stretched and then condensed. We know that the universe is about 13.7 billion years old, And first we have the protons and neutrons, which then joins to atoms. And here somewhere the first stars appeared. When they really appeared, that is still under discussion. Proto-galaxies, finally galaxies, and we know that's life, at least in one place in our universe, for at least 3.5 billion years. But the steps to life, the origin of the biogenic element, was much earlier. So probably very early at the when the universe was about 1 billion years old, and then also the elements might have joined to molecules, which are called the biogenic molecules. So the formation of the elements of life, that actually happened in the stars through nuclear fusion, hydrogen burning, and further burning to becoming more and more heavy mass elements. And up to iron, these processes are really in the stars. But in order to have even more heavy elements, which are required as some rare elements in life processes, and that needs supernova. And you will hear that in more detail during the lecture. But the biogenic elements are carbon, hydrogen, oxygen, nitrogen, sulfur, phosphorus. These are those which make the bulk of the living material. And here you see the acronym. So we can really say that life is composed from the ashes of previous stars, because there is a kind of cycling of the stars. But now we have the elements. They have to form molecules. And this happens mainly in the interstellar medium or in circumstellar clouds. And many of these elements have been identified by telescopes now. And some of the most important are the hydrogen cyanide, formic acid, formaldehyde complex carbon compounds. Especially these elements look like they are poisonous. These molecules look as if they are poisonous, but actually they give rise to different important biological molecules like the amino acids and the sugars. And we found also very complex compounds there. And so you see from the diffusion interstellar medium, the cloud condenses. Finally, we have the birth of the star. Here we have the planetesimals around the star, and especially those parts from the outer planetary system, the comets and the asteroids. They provide them when they somehow impact on a planet, and here's an example, is our Earth. Then they bring a lot of organic molecules. And finally, after billions of years, the star will grow and grow, and in our case, our sun will become a red giant, and then it's a cycle. It goes again in the same cycle. So it's somehow the organic molecules and the elements that are finally produced are the product of several cycles of solar, stellar origin coming and going. So in order to put the story together, how has it happened on Earth, or how do we think that the steps to life happened on Earth? First, we had the organics from space, as I told you, but at the same time, there's a lot of abiotic synthesis of complex organic molecules on the early Earth, and you will hear about that also in detail, which forms then somehow what we call a prebiotic soup, but that necessarily does not need to be a ocean or soup. It can be somehow in isolated compartments where then more prebiotic polymers are started, and somewhere, and that's the black box, we have the origin of life. We think on Earth, it went through an RNA world, and then finally what we observe today, the DNA protein world of modern chemistry. But we should not forget that this has started on Earth very early, probably during the first billion years of the existence of the Earth. So this protein DNA world is already at least 3.5 billion years old. So at the moment, what we can say is that the Earth is the only planet known to harbor life. And that was written in the famous book of Carl Sagan, The Pale Blue Dot. And that showed if you move further and further away, like the Voyager spacecraft and Pioneer spacecraft, then the Earth becomes only visible as a very little pale blue dot. But the question is the Earth alone the only one, or do we just don't know whether there is another habitable and inhabited planet? So is the Earth one of the planets that harbor life, and are there others? And that's, of course, also the question of astrobiology. So one has first to go into our solar system and search whether other planets provide conditions that are supportive for life. And I've here listed all the missions which are currently two planets or moons or bodies in our solar system. So we have mission to Mercury, the messenger mission. ESA is planning another mission. We have Venus Express to Venus. We have 3 orbiters around Mars, Mars Express, the European one, and then Odyssey and Mars Reconnaissance Orbiter from NASA, and 2 Mars Exploration Rover. You have witnessed certainly how long they already, the rovers, are active on Mars, at least one of them. Phoenix, who landed in the polar region. It was not a rover, just a station. And Mars Science Laboratory, which is just now working and landed in August this year on Mars. And I would be so happy to add here ExoMars, which is a European mission planned, and we very much hope that that will realize in 2018. Jupiter has been visited by Galileo, brought us very interesting data also about the moon Europa, and there will be a next European mission to the icy moons of Jupiter. It's called JUICE. Cassini-Huygens is still active and brought us very interesting results, especially of the moon Titan, where the Huygens probe landed on Huygens and showed us data of the interesting complex chemistry, that organic chemistry that's going on that moon. And then we have Rosetta with a lander that goes to a comet, Churyumov-Gerasimenko, and that will land, I think, in 2014. So there's a lot going on in our solar system, where we want to investigate whether these planets are habitable or provide preconditions for life. But now we have to ask what we are looking for. So what is common to all life forms on Earth? And here you see that we have microscopic life, and we have big trees, and we have all different variations. But what's interesting, if you look under the microscope for the cells, or even with the molecular biology, you find that there's many things common to all these life forms. All life forms are built out of cells, so life is compartmentalized. All life forms base their whole metabolism on carbon-based chemistry. In all life, the genetic code that is in the nucleic acid is the same. We have the same set of amino acids in the proteins that are the workers of the cells. The same machinery how this information is transcribed into the daughter cells, and the same machinery how this information is translated into proteins. And we have interactive communities, food chains. So that's the same for all these large variety of different life forms on Earth. So in order to come down, what are the really basic requirements for life? We have 3 requirements. One is we need what we have to search that must be available in order to be habitable habitable. And that is first a carbon source. So some molecules, and you see here the complex chain of a hemoglobin molecule. Then we need an energy source. It can be the sun, but it can also be other redox systems, for instance, minerals or rocks, some chemical redox systems, maybe also physical one, others, and water. And water in liquid form. And why water? Water has so many functions. You think it's only a solvent, but it's not only a solvent, it is a selective solvent, because depending on the molecule, if you have hydrophilic groups or hydrophobic groups, the molecules can be oriented. It's a diffusion milieu. It's a reaction partner in many metabolisms, for instance, in photosynthesis. In photosynthesis, water is split, the oxygen goes in the atmosphere, and the hydrogen is used for reducing the CO2 and making it a biomolecule. It forms clay. Clay is, we think, it's a very important substance in the prebiotic processes before life started. It's a dipole molecule. It structures the biopolymers I showed you just before, the hemoglobin molecule. And this structure, the three-dimensional structure of the proteins, can only be stable if there are water molecules in between. And it is a heat dissipator. So the question is, where shall we look in our solar system where the right temperature is to provide liquid water? So liquid water is the precondition for habitability. And one has done this, made models and calculated where could be liquid water on the surface of a planet as a function of the mass of the star and the distance from the star. And here you see the habitable zone, and the mass of the star is relative, where 1 is the mass of our sun. And you see this is our solar system, that Earth, of course, is in the center of the habitable zone, but also Venus is close to, maybe somewhere in the early time, and Mars, depending on the model, is sometimes outside and sometimes close to in the habitable zone. And you see if the star has lower mass, for instance an M star, then the habitable zone has a much lower distance. Here 1 is the distance of our sun, it's called of our Earth, then Earth from the sun, and that's called an astronomical unit. So this seems that water is really the prerequisite where we have to look for. However, water might not be enough. We have the example of life on Earth, and Charles Coquerel and Francis Wester, who are also participating as lecturers in this course, have set up a postulate to assess habitability. And they say that we have to find at least one example on Earth which could live under these conditions which we find beyond the Earth. So a planetary body is or was habitable if the physical and chemical conditions of the environment under consideration match with the physiological requirements of at least one type of microorganism on Earth. Why microorganisms? If you look outside, you don't see microorganisms. The reason is why we select microorganisms as a reference for habitability is that microorganisms were the first that appeared on Earth. The oldest fossils, microfossils, are 3.8 billion years old, and some think even 3.8 billion years old fossils, microfossils, could indicate that life existed already. So it took very long time, billions of years, 1 to 2 billion years, until the first more complex organisms appeared. So microorganisms seem to be the first that appear on a planet. We find them everywhere. We find them in water, we find them deep in the ocean, we find them deep in the subsurface, we find them in the atmosphere, we find them everywhere. So they are ubiquitous. And they inhabit extreme niches, and we will hear about that also another talk, at least 1 or 2 talks, how microorganisms can adapt to different environmental conditions, extreme conditions, high temperatures, low temperatures, oxygen atmosphere, anoxic atmosphere, and so on. That does not mean that the microorganisms can live under all these conditions, but they are specified either to cold temperatures or to high temperatures, either to low pH or to high pH. So they are very, very specialist, but they have settled the whole Earth, deep subsurface, oceans, atmosphere. So that means microorganisms are really everywhere on the Earth, and if we want to look somewhere, we should look for microorganisms. So with this, one could define where are habitable sites in our solar system and beyond. And I refer here to a paper in Astronomical and Astrophysical Reviews that appeared in 2009 by Helmut Lammer and co-authors. And they say the first class of habitats is like our Earth. So based on the conditions that were life could appear on the planet and evolve to complex multicellular life forms like it is on Earth. So the second Earth. That's why we are all, also the astronomers are now looking for a second Earth in extrasolar planets. So that would be the ideal example. But we have another example which is not so favorable for life, like Mars. And Mars is one of the planets we are looking whether life has, maybe if it has appeared once on Mars, whether it, during the history from a more wet planet to a colder and drier planet, life has either been extinguished or retreated in some subsurface oasis. So that means the second class of habitats are bodies where life could have appeared, where the conditions have provided good conditions for the appearance of life, but then due to other conditions, external conditions, internal conditions, the planet is too small, too far away from the sun, or whatsoever, they either became too hot or too cold, and so only conditions were favorable to develop simple unicellular life. The third class, there's an example that is our planet, our moon, Jupiter moon Europa. Here we have liquid water. We have liquid water under an ice cover and in connection with a soil regolith, not regolith, lithosphere, the lithosphere. And here you have, for instance, liquid water as energy source. You can take minerals, and the carbon is probably from infalling comets and meteorites and so on. So we have all the ingredients, but nobody knows at the moment whether this is still favorable for the conditions of life. So bodies where subsurface water oceans exist that interact directly with the silicate-rich core. They are of special interest, and we hope that the European mission JUICE will bring us more insight into the habitability of Europa. And the last class are those who have also liquid water, but not on the surface, but below a very thick ice cover, and also connected only to an ice cover. And these are, for instance, the large moons, as example is Enceladus, but also the other icy moons of Jupiter. And so at the moment we do not know whether these conditions are already favorable or not, whether that's really a habitable zone. So now I talked about the habitable zone around our sun. Here we have the habitable zone, our sun, where we have Mars, Venus, and the Earth. And the question is now, the sun is here in our galaxy located, and the question is whether we have also a habitable zone in our galaxy, the habitable zone around the galactic center, and what are the conditions for this. And here I refer to a paper by Lineweaver, Fenner and Gibson from 2004, and they have established some conditions, requirements for a habitable zone in our galaxy. First, we need, of course, a host star, because only planets that orbit around the star can be supportive of life. The star itself is much too hot, so that cannot support life. Enough heavy elements to form terrestrial planets. I told also about the requirements for life, that we need all the heavy elements, so hydrogen and helium, which were produced in the first category of stars, is not enough. So we need several cycles of stars in order to have all the heavy elements. We need time for biological evolution, because if you take life on Earth, it took about 3.5 billion years for life from simple microorganisms to develop to a highly evolved, complex forms of life. And the environment should be free of supernovae, because they could be very dramatic and destroy a whole planetary system. So based on these assumptions, they have set up a kind of zone around our galactic center. So we have here the distance from the galactic center. Our sun is about 8 point something kilopascal distant from the galactic center. And here is a time scale, the time before present. So that's now, and here the galaxy has formed about 12 billion years ago. And you see the green zone, and that is the habitable zone for simple microbial life compared to that life that appeared 3.5 billion years already on our Earth. And what you can see is it should not be too close to the galactic center, because there are too many supernovae. That's a very reactive region. Further out, there are not all the heavy elements, so the astronomers call metal everything that's heavier than helium. And it could go until today. So there could still be now, or let's say at least 1 billion old stellar systems which already could have witnessing the origin of life. So microbial life could even be in very young planetary systems, extrasolar planetary systems now. But in order to develop to complex and, let's say, intelligent life, it takes much more longer, because we know on Earth it took about 3 billion years. So then this habitable zone for complex life, intelligent life, maybe communicating life, is much smaller. So the time, it should be at least 4 billion years old that they had the time to develop these forms. And that is what is important if you also are interested in safety in search for intelligent life. Yeah, and with this, I would close with another Nobel laureate, Joshua Lederberg, who really explained why we need to, biology also needs to go into space and to look for other forms of life and to understand how life originates within the context of cosmic evolution. And he compares this with the physics and the chemistry. And he says the exploration of space has widened the horizon of the physical world. The concepts of mass and energy are valid throughout the universe. And also for chemistry, it's the same. It has to lead to the generalization of chemistry. The spectra of the stars testify the universality of the concepts of chemistry. And what's with biology? It has a potential to inspire biology and to find out, if we find another form of life, if we find out how life originates, then we can build the foundations for the construction and testing of a meaningful axiom to support a theory of life. Because it's only possible to develop a theory of life if you have more than one example of life. And that's what we are looking for. And if you are interested in further readings, there are several books. Some are not so recent. Astrobiology, The Quest for the Conditions of Life, was one of the first books on astrobiology. It's from 2002, so I even don't know it's available on the shelf, but you have it it's still available on the DLR website. You can load the whole book down under this website. Then another book, Looking for Life, Searching the Solar System, by Paul Clancy, André Bracq, and myself. Cambridge University, 2005. Then there are lectures in astrobiology, volume 1 and volume 2, with a French group. Muriel Garbeau was the main editor of this, and this gives also the whole story, part volume 1, from prebiotic chemistry to the origin of life, and then volume 2, it goes further into the solar system. This is a book which is from the first course of ABCNet. The lectures of the first course of ABCNet are here published. And then a very good introduction into astrobiology is this book from Cambridge University, edited by Ernst Gilmore and Mark Sepson, which is really for the beginners a very good book. And if you want to learn more, then last year appeared the Encyclopedia of Astrobiology from Springer with a lot of editors and authors. And I think this closes my lecture. Thank you very much.